Okay, this is the midterm from spring of 2017. This will cover everything from electric force to magnetic force being the Lorentz force law, not sources of magnetic fields or anything like that. Okay, so the first question asks, which one of the following statements best explains why a constant magnetic field can do no work on a moving charged particle? Well, option 1 says the field is conservative. That can't be true because so is the electric field. E is also conservative. The next choice says the magnetic force is a velocity-dependent force. Well, there's nothing really in there that has anything to do with work, so that's not a good choice. It's kind of it's not a good choice. The magnetic field is a vector and work is a scalar quantity. Well, so is the electric field. The electric field is also a vector and work is still a scalar quantity because work comes from the dot product of the force and the displacement. So that makes no sense. The magnetic force is always perpendicular to the velocity of the particle. Yes, that is your answer choice. Because work, remember, is the integral of F dot ds. And the work, so if the force is perpendicular to the displacement, the dot product is 0. And the magnetic force given by the Lorentz force law and the vector cross product, the magnetic force by definition has to be perpendicular to both the velocity and the magnetic field, so therefore work is 0. And that is your explanation. That is the property of the cross product. And the next choice says the electric field associated with the particle cancels the effect of the magnetic field on the particle. That has no meaning. So the sketch below shows cross-sections of equipotential surfaces between two charged conductors that are shown in solid gray. So here's one conductor, here's the other conductor. These are charged. We don't know which is positive and which is negative from the beginning, so let's just keep reading. Various points on the equipotential surface near the conductor are labeled A, B, C, and I. What is the direction of the electric field at B? Well, given that this is positive potential, this is 0, and this is negative, this must be the positive charge, and this must be the negative charge over here. So I zoomed in a little bit, that'll help some. So the higher potential is closer to the positive charge, the lower potential is closer to the negative charge. And again, all of this potential stuff is just relative. So whereas this is what, 50 volts, and this is, because that's negative 70, so negative 80 volts. So 50 and 80, so that's 130 volt potential difference. It doesn't matter. This could be 130 volts and this could be 0. As long as the difference between is 130 volts, that's all that matters. So what is the direction of the electric field at B? B is right here. If you remember, the equation for the electric field is the negative gradient of the potential, or if we just want to talk about it in terms of one dimension, Ex, so that's negative d dx of the potential. So the negative derivative of the potential. That is the negative rate of change of potential with respect to position. In other words, how much does potential change per some small distance dx? So the greater the change of potential, the stronger the electric field. But we're not even asking about the magnitude, we're asking about the direction. So this means as the potential is increasing, as the rate of change is positive, the electric field is negative. So the electric field points in the opposite direction of the increasing potential. So if I go to point B and say which way does it increase, well, potential increases as I move this way, so electric field must point in that direction, which is towards D. Now you could look at it from another perspective. We already determined that this is the positive charge here, and this is the negative charge because the higher potential here is here, the lower potential is there, so this must be positive, this must be negative. The electric field points away from the positive charge, right? So we know that the electric field has to be towards D. If the question asks what is the magnitude of E, the electric field, and I can go by the vector bar, I can go ahead and say that, or well, let's just do it like this: the magnitude of EX, and I can go ahead and say it's in the X direction because we know it's going to be either left or right. What is the magnitude? Well, it's going to be the negative change of, well, we're just looking at the magnitude, so the negative gives you direction. So what we just need to see is the rate of change of potential with respect to X. And since this is a very easy thing, this is a very constantly changing electric field because I'm stepping down by 10 volts every 0.1 meter. So I can say this is equal to, only in this specialized case, the magnitude of negative change in voltage over change in position. So it's the negative change in voltage from D to this point, plus 10 to 0. So it's going to be negative 10 volts. So I'm losing 10 volts as I go from B to this line here, not all the way to D, but just to this line. And that change in position, if it's 0.4 meters across 1, 2, 3, 4 divisions, then it will be 0.1 meter across 1 division. So I take the absolute value, so I can ignore the sign. That's 10 divided by 0.1. That equals 100 volts per meter. If the question were to ask which of these labeled points has the greatest magnitude of the electric field, that's going to be I, because see how between every one of these lines is 10 volts. So this is 10 volts over a very tiny amount of space. If this is 0.1 meter, this is what, 0.02 meters, something like that. The electric field might be the weakest at, I don't know, maybe E is the largest distance between those two equipotential lines. If you wanted to know something about the direction of the field, this is easy. The field is always perpendicular to the equipotential lines here, but once these lines start getting a little curved and weird, the field must curve upward and end up at the negative charge. I didn't do that quite well enough because you see it's perpendicular at these points, but here it starts to curve. Here it's perpendicular, and it must curve over here and end at the negative charge. So it curved up and then it curved back. Why? Because I'm trying to maintain this perpendicular intersection with the equipotential lines. So over here is going to be more straightforward. It's going to start curving downward here. Again, it's going to curve more. Okay? So everywhere it crosses the equipotential line, it must be perpendicular. If I want to go way down here, I can say right here it starts to curve up. And right here it starts to curve back. Here the field is going to be something like this. And that would continue on in this direction. Alright, so here we have a situation where we have an electron traveling horizontally and enters a region of uniform electric field directed into the plane of the paper. Which one of the following phrases most accurately describes the motion of the electron once it has entered the field? So the electric field is into the page. The electron is going to go in the opposite direction of the electric field, so that means it's going to curve out of page. The electron feels an electric force that's equal to Q times E. Since Q is negative, that's going to be negative E times the electric field. So it's going to be in the negative direction of the negative direction of the electric field. If the electric field goes into the page, the force must go out of the page. So that gets rid of this, upward, downward, into the page. We know it can't be into the page, so it's got to be out of the page. One of these two options. Now, this force is going to be constant as long as the electron is in the field. So it's going to curve upward, and just like throwing a ball with some velocity in a gravitational field, it's going to experience a constant force. That trajectory is going to be parabolic. So here, the electron is curving out of the page, but it's going to curve out in a parabolic trajectory. So this next problem asks about an electron moving in a uniform magnetic field directed into the plane of the page, just as we saw before. Instead of electric field, it's magnetic. And we are going to assess the direction and the trajectory. Well, the Lorentz force law tells us that the force of the magnetic force is equal to Q V cross B. Using our right hand rule, remember our hand goes in the direction of the electron's velocity. We curl it in the direction of the magnetic field, and our thumb points in the direction of the force. Or put another way, we can say we point our index finger in the direction of the velocity. Our middle finger comes at a right angle in the direction of the field, which is into the page, and our thumb is the direction of the force. So in that case, the force is upward. The magnetic force experienced here is upward. Velocity is to the right. The field is into the page. The force is upward. So all of these are not correct. So now, what is the shape of the trajectory? So if this were a constant force, it would be a parabolic trajectory, just like with the electric field. But it's not a constant force because the electron comes in with some velocity, and at some point later, as it's being accelerated upward, it starts to curve like this. Now its velocity is in this direction. We'll do the right-hand rule again. Velocity, now at an upward angle. Field into the page. Force is now at an angle. Sorry, I didn't draw it up here. Force is upward here. So as it continues along this trajectory, at this point, its velocity is straight up. Field is still into the page. So now the force is to the left. So the result is that it's going to move in a circle as the direction of the magnetic force changes throughout the trajectory. Okay, so back to Gauss's law. Rank the electric fluxes through each of the Gaussian surfaces in the figure from largest to smallest, displaying cases of equality. So Gauss's law says that the electric flux, now I'm putting the little subscript E here for electric because we're about to get into magnetic flux. But in this case, it's just the electric flux is equal to the charge enclosed over some constant epsilon naught. So if we just ignore the epsilon naught, we can say that the electric flux is proportional to charge enclosed. Well, which one has the most charge enclosed? So 3Q is the most. What about 4Q? Well, it's outside of the Gaussian surface, so nothing is enclosed by the Gaussian surface, so this is 0. And these surfaces, they're different shapes, but they both have Q. They both enclose charge Q, so the electric flux there is going to be equal. So if we're ranking this, we can say that the flux in C is the most, so it's greater than the flux in part A, which is equal to the flux in part B. These two are equal because they enclose the same charge. And these are greater than the flux in D, which is equal to 0. So in this case, we have a positive charge that is moving from this point to that point, closer to the other positive charge B. So would A be moved to higher or lower electric potential? So that is going to be, well, you can look at it from several different ways. It's going to be higher because the higher potential is closer to the positive charge. What is it? What if it were a negatively charged particle you're moving from here to here? Doesn't matter because the potential is set up by the field. So potential is equal to negative the electric field dot ds, where d is the displacement. So the field set up by this positive charge, and if we're just moving along path 2, this is the simplest case. So the field is in this direction, and the displacement S is in this direction. So this is equal to negative ES cosine of theta. I integrated along the path. E is, well, we can't say E is we can't say this. I take that back because E is varying along this path. So E is not constant. But fortunately, the question is not asking us to calculate the actual change in potential. It's just asking us, is it higher or lower? So let's look at, so that's negative the integral of E cosine theta ds. I'm going to have to integrate theta in with this and everything too. But we know that theta in this case is just, well, we don't have to integrate theta because it's constant. And it's going to be constant 180. So this is negative integral of E times negative 1 ds, or just the integral of E ds, which is positive. And I should have put the change in potential because as we're moving from here to here, the change is positive, it's increasing. Moving to closer to the positive charge. Notice that this does not depend on the sign of this charge at all. If you move from this point to that point, you're moving to a point of higher potential. You don't have to have a charge in here. You could have a negative charge, whatever. The potential difference between 2 points surrounding this point charge has nothing to do with whatever other charge you put in. It's set up completely by the change in field. The potential increases as we get closer to the positive charge. Another way to look at it is, you may remember we brought this up earlier, the electric field is negative d dx of the potential. So the field points in, negative means opposite direction. The opposite direction, I should put vector bar, the opposite direction of, and I should put I hat there, the electric field points in the opposite direction of increasing voltage. So we know field points this direction away from the positive charge, so the potential must increase in the opposite direction. So part B says, is the work done by the electric field due to B positive, negative, or 0? Well, work is equal to the, we define work as F dot ds, right? The force is in this direction because the force is acting upon this positive charge to push it away. The displacement is in this direction, so again we have this 180 degree difference, so it equals negative some number. The work is negative. What does this mean physically? It means that to get this charge from here to here, some outside force, I'll call it force applied, has to work on this charge against the electric force in order to move it over here. So that means the electric force does negative work. Another way to look at it is that the work done by the electric force is conservative, so that equals negative change in potential. And potential is equal to Q delta V, so this is negative Q delta V. We already said that this is positive because it's increasing, so that means the work of the electric force is negative. C, rank the paths according to the work our force does. The work our force, so this implies the force applied, does from greatest, well, it doesn't matter because force is path independent. Work is path independent. So let's say I'm pushing along path 1, so at some point I'm pushing downward right here, but the displacement is in this direction. So add all these things up, the positive, and here the displacement is negative in the y direction, and then it turns around and becomes positive in the y direction. All these things add together, and you end up with the same result as if you went right from here to here. It's path independent. So work 1 equals work 2 equals work 3. Number 7, determine the initial direction of the deflection of the charged particles as they enter the magnetic field shown in the picture. Now, notice that says initial direction because as the particle travels through the magnetic field, that magnetic force is going to change. We already talked about that. So we're just we're just applying the right-hand rule to the Lorentz force law, and we're going to find the direction of the force. So in case A, the velocity is to the right, the field is into the page, the force is up. If I use the two-finger method, velocity is to the right, the field is into the page, tapping with my middle finger, the force is up. And it's a positive charge, so that is how it works. Here, the velocity is to the left, or I point my fingers to the left, the field is up. So I rotate, I need to keep my fingers pointing in the direction of the velocity, which is left. So I rotate my fingers in a way that I can curl them up, and then the force is down into the page. Or using the two-finger, three-finger, I guess, method. For velocity, sorry, it's hard to see here. Velocity is to the left, the field is up, so my thumb points down into the page. So I could say that the force is into the page. I was about to say that, but I noticed one thing. This is a negative charge. So I have to reverse that. So remember, this right-hand rule works only for positive charges. If it's a negative charge, you flip the direction, and so now the force from the magnetic field is out of the page. It's just because the charge is negative. Okay, so in this next situation, the velocity is this way, the magnetic field is in the opposite direction of FB equals 0. Remember the magnitude of the magnetic force is QVB sine of theta, where theta is the angle between V and B. In this case, the angle is 180 degrees. Sine of 180 degrees is 0. So here's a situation where we don't have right angles. So the velocity is upward. My fingers in the direction of the velocity, I have to bend them to this angle that is upward. So I'm going to rotate my hand around, keeping my fingers pointed in the direction of the initial velocity. I curl them in the direction of the magnetic field, which is I curl them only 45 degrees this time, not 90, and my thumb then is going to point straight down. It's going to be into the page. Or using the three-finger method, velocity, magnetic field, and the thumb goes into the page. So problem 8. This is trusted old favorite that I'm sure you know how to work by now. This is just a vector addition problem. You have 3 charges, and you want to find, in unit vector notation in terms of KD and Q, you want to find the net force vector on the third point charge plus Q. So I'm going to label these charges 1, 2, and 3 for convenience, and I'm going to refer to them as such. So let me draw a free body diagram. X and Y axes. The force on charge Q, so this is charge 3. Remember, free body diagram takes whatever object is being acted upon, and that is the central focus of the free body diagram. I erase that arrow because I don't want to put too many additional arrows on the free body diagram. So it's going to experience 2 forces. One is from charge 1 on 3. Force from 1 on to 3 is going to be repelling this charge because they're both positive, so it's going to be straight up. And I'm going to call that force 1, 3. So it's the force from charge 1 onto charge 3. The other, let me draw it here too. The other force is going to be from charge 2, but this is negative, so it's going to be an attractive force. It's going to be downward like that. Force from 2 onto 3. I'll call it force 2, 3. And you'll see that if both of these forces are directed right along the line connecting these charges, then the forces are going to take the same, are going to make the same angles that that you can derive from this triangle here. So I'll call this theta. Why did I choose that to be theta? I don't know. It doesn't matter. I could have labeled anyone. I could have labeled this angle 2, but then I would have to say, 90 minus theta, whatever. Okay, so let me draw another free body diagram, as is the custom. F13. This is going to be F23x and F23y. So I have 3 force components I have to add. So let me go to my usual table. In the x direction, all I have is F23x, which is just equal to the magnitude of F23 cosine of theta. Okay, because this is opposite side of the triangle. And on the y side, I have negative F23y, and negative just because I'm dealing with magnitudes here. So I have to insert the negative next to the magnitude to indicate direction. So this is negative F23 cosine of theta because it's the adjacent side of that triangle. And then I also have this positive F13. So the sum of the forces in the x direction is just F23 sine of theta. Now, if we note Coulomb's law, the magnitude of the electric force is just K Q1 Q2 over R12 squared. We can say this is equal to K Q1 Q3 in this case, because the other charge is Q3, over R13 squared, and sine of theta. So this is our generalized expression that comes from Coulomb's law. But now we note that Q1 equals Q, 2Q, 2 capital Q, because that's the magnitude of this charge, and Q3 is equal to capital 1Q. We know that R13 is equal to just D. Now we don't know anything about theta. Yes, you could say that because both sides are equal, theta is 45 degrees. I get that. We could do that. This is a slightly more elegant way to do it, to say sine of theta is equal to opposite, which is D, the opposite side of that angle, over the hypotenuse, which is the square root of D squared plus D squared. And that's going to equal D over square root of 2D, which is just 1 over square root of 2. Now you could, like mathematicians, get that radical out of the denominator and you'd have square root of 2 over 2. I don't know, that makes the math just a little bit more messy for me, so I can fix all those things at the end. Let me right now plug in for these values. Q1 is 2Q times the other charge, Q3 is plus Q. The distance R13 is D, so that's just D squared. And then this sine of theta is 1 over square root of 2. So I can say the sum of the forces in the x direction is just K Q squared over D squared 2 over square root of 2. Now this is where I see where this is going. There's going to be a similar expression in our other terms as well. I could just say what is F, I call something like F naught. What is that? That's just a dummy variable, 2 over square root of 2, where F naught is K Q squared over D squared. Okay, so I've got Fx. You didn't have to simplify do this little expression. This is just a way to make it cleaner. It's not that important. But moving on to the sum of the forces in the y direction. So I'll start with the positive one first. So that's F13 minus F23 cosine of theta. This is equal to the magnitude of the force, F13, given by Coulomb's law, is K Q1 Q3 over R13 squared, minus, from Coulomb's law, K Q2 Q3 over R23 squared cosine of theta. Well, going back over here, cosine of theta is again D over the hypotenuse, root 2D. That is also 1 over square root of 2, which you know because the angle is 45 degrees, so cosine of theta equals sine of theta. You could have done that. You could have made that realization that theta is 45 degrees. That would be fine too. Let me go ahead and plug in the numbers for Q1 and Q3. So this is K times Q1, which I'm calling, I wrote this down, 2Q times Q3, which is just positive Q, over the distance between 1 and 3, is D squared. Cosine of theta, or excuse me, not there yet, Q1 and 3. Minus K times charge 2, which is negative Q. Well, let's not put that negative in there. If we go back to Coulomb's law, I should have stated that this is the absolute value. And the reason I'm ignoring that negative charge is because I already have this negative here to indicate direction. So the magnitude, according to Coulomb's law, is just going to depend on the magnitude of the charges. So that's Q times Q3 is also q over the distance between the two, which now you remember is root 2d. Squared. Now we have to put in this cosine of theta term. That's 1 over root 2. So let's simplify all this stuff. Well, I can pull a kq squared over d squared from every term. In the first term, that's just going to be, you're left with just 2. That's the only thing, q over d squared, so you're just left with q. Minus kq squared over d squared, but then I have the square root of 2, which I then square, and I also have this 1 over root 2 again, so that's 1 over 2 square root of 2. And if you want to make the fancy little simplification, I can say Fy is equal to F naught, where this is what I called F naught, 2 minus 1 over 2 square root of 2. So the question asks for your final answer in unit vector notation. So the sum of all the forces equals Fx I hat plus Fy j hat. And that's just going to equal F naught 2 over root 2 I hat plus F naught 2 minus 1 over 2 root 2 j hat. And of course you can factor out the F naught. So this is 2 over root 2 I hat plus 2 minus 1 over 2 root 2, oops, j hat. And that's your final answer. If you wanted to, you could throw this in your calculator and put a decimal down. That would be fine too. Okay, so this is a particle attached to a string. It's swinging around in a kind of arced position, kind of an arced path, because the electric field is pushing this way, so the force experienced on the particle is in this direction. If the string wasn't here, the particle would just shoot out to the right in the direction of the field. But the string is here, so that means the string provides a tension, a centripetal force. That means the particle will move to the right, but it will have to move in this arced fashion. How much work does the string do? Well, it does 0, because remember, in the centripetal force will always do 0 work, because the force is perpendicular to the displacement. So, how do we go about this? Well, the easiest way to think about it is this is the exact same problem as if I'm given some electric field. We worked several problems like this in class. Let's say you've got some uniform electric field pointing to the right, and you want to go from this position to that position. What is the speed of the particle? Well, we can find that the sum of work done is equal to the change in kinetic energy. So the work done in moving from point A to point B is just going to be exactly the same as the work done going from point A to point C, because the only thing that matters is the work done in the direction of the field. So let's go to let's look at the definition of work, because this equals the work done by the electric force. That equals F dot ds. That's from the definition of work. We could find this angle. We'd have to do some complicated geometry, and to us, maybe the geometry is not even impossible. I don't know, because I don't really care. All I care about is the force along, is the displacement along the direction of the force, or the force is QE, so E dot ds. The only thing, the result of that dot product is going to be E times this section of the displacement. I'll call this Sx, the displacement along the x direction. Same here or same here. Doesn't matter. So this is going to equal Q E S X. The field is uniform, so you can pull that out of the integral dot ds. And let me just show this in more steps. So this is going to be E dot displacement S. Once we integrate over ds, we still have the dot product E dot ds. And oh, by the way, I should call this phi, not theta, because we already have theta here. These are not equal angles. So if this is S, this is E, this is just equal to Q E cosine, excuse me, Q E S cosine of phi. And like I said, finding phi is going to be kind of difficult. But I can say Q E S X is equal to the change in kinetic energy. Why did I do SX? Because S cosine of phi, given this geometric relationship, is going to be equal to SX. And I think I can find SX a little bit more simply, given the geometry of our problem. So we know that the length of the, okay, this is a little too exaggerated, but the length of the string is L. So that's going to be this length here from the point P to the initial position. And we also know point P to the initial position here, or the final position, is also going to be L. SX then is going to be just this segment here, the horizontal distance traveled. So I know this is angle theta. I can say the cosine of angle theta is equal to the adjacent of this right triangle here, which the adjacent leg of that triangle is just L minus SX, because L is the total length and SX is just that additional x direction movement. And the hypotenuse then is L. So I can solve for Sx, so Sx is equal to L minus L cosine of theta. If I bring that L over there and move things around, so that's equal to L times 1 minus cosine of theta. So now I have an expression for Sx. I can put that in. I can say the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared, Q E L 1 minus cosine of theta. I just plugged in for Sx. The initial velocity, it starts at rest, is 0. So 1/2 mv final squared is equal to Q E L 1 minus cosine of theta. So Vf is just equal to the square root of 2Q E L 1 minus cosine of theta over m. We're given L, we're given mass, we're given Q. And the Q here is just the would be just the magnitude. Oh, looks like I noticed a problem from this. Oh, I see in my key. Yes, this was corrected to be positive 2Q. That's my mistake. I'll have to send an email to remind you that, because, and that's got to make sense to you, because the negative charge cannot move in the direction of the electric field. That was a problem with pasting the problem in. So this is a positive charge. It has to be positive if it's moving in the direction of the field. So yeah, so all this stuff with the string, I mean, there's some geometry involved here, but this is essentially, going back to this, it's the same idea that only the displacement along the direction of the field is going to contribute to the work at all. So this displacement perpendicular to the field it contributes nothing to the work at all. So the total work is equal to change in kinetic energy. It's just due to that displacement. This next problem is asking you to calculate power delivered to each resistor in the circuit shown in the figure below. So this is more of a simple circuit, so we don't have these multiple loops, so we don't have to apply Kirchhoff's loop rules or anything like that. We're just going to reduce this down to one equivalent resistor and then build the circuit back up. We need to find the current through each one of these resistors because we know that power is equal to I squared R. So if we have the current and the resistance, we know the power delivered to each one of these resistors. These two are going to be easy because we'll find them first. Or we could say power is equal to IV. So if we know the voltage drop across those resistors, we can find the power, but we still need to know the current. Or we could say V squared over R. So I suppose if we just find the voltage drop across each one of them, we can do that. That might be the easiest, quickest route. So the first thing you do, and when you're condensing these circuits, take the time to just draw out the new circuit so that you know what you're doing. So this is 1, 2, 3, 4. So this is, I'm going to call this R2, R13, and R4. I've combined these two resistors. So R13, you have to work with the parallel first, and then proceed. Make this a little bigger. R13, since these two are in parallel, I have to add their reciprocals. So 1 over R1 plus 1 over R3, and take the inverse of that. So that equals 1 over 1 ohm plus 1 over 3 ohms. 1 plus 1/3, so that's 4/3. Take the reciprocal. R13 is equal to 3/4. You could do the decimal if you wanted to. It's just I solved a fraction, so I did that. So, well, I could go ahead and find the voltage drop, but yeah, you know what? Why don't we do this? I did it differently before, where I found the current first, but let's just go find the voltage drop across resistor 1,3. So the voltage drop across 1,3 is equal to the, oh, can't do that, got to find the current through 1,3. Because V13 is equal to I, the current through, times the resistance. We have to find the current first. Okay, so let's condense all of these down to R1, 2, 3, 4. So R1, 2, 3, 4, these three are now in series, so I can just add them, R13 plus R2 plus R4. So that equals 3/4 ohms plus 2 ohms plus 4 ohms, so that's 6 3/4. So R1, 2, 3, 4 is equal to 6.75 ohms. So what's the current through this resistor? I1, 2, 3, 4, that's the current through this very simplified circuit. It's just V1, 2, 3, 4 over R1, 2, 3, 4, or 18 volts over 6.75 ohms. That equals 2.67 amps. And we will also note that this current, I1, 2, 3, 4, because all of these are in series, all of these have to be the same. So that equals R2 equals R4, I'm sorry, equals I2 equals I4, and equals I13. So now I have the current through this circuit. If I go back and say R2, R13, and R4, the voltage drop, which I can now measure across resistors 1, 3, that's the equivalent resistors to these two in parallel, V13 is equal to I13 R13. So that's equal to I13, we found it up here above, 2.67 amps, times R13, which is 3/4 ohms. So what that's 2 and 2/3. Well, all right, let me just 2.67 times 0.75. So that's about 2 volts. Okay. That voltage is going to be the same as the voltage drop across resistor 1, and it's going to be the same as the voltage drop across resistor 3. Because in parallel, this voltage is the same as that voltage. So the power in resistor 1 is V squared over R, V1 over R1. So that will be 2 volts over 3 ohms. The power through resistor 1 then is 0.67 watts. I'm sorry, this is squared, so that would be 4/3. What am I thinking? Okay, this is 4 over 1. Resistor 1 has 1 ohm and V squared, so that's 4 volts squared over 1 ohm, so that is 4 watts. Sorry. Well, in resistor 2, again, V2 squared over R2 now. So again, that's 2 volts because the voltage across resistor 2 is the same as 3. The voltage across resistor 3 is the same as the voltage across resistor 1. And that is 3 ohms. So this is going to be 2 squared, that's 4/3 watts, or 1.33 watts. Okay, well, what about these two resistors? We don't have the voltage drop across each one of them. They're going to all add up to 18, the voltage of the battery, but we do have the current through it. So P2 is I2 squared R2, and the current through R2 is going to be the same as the current through the whole circuit, so that's 2.67 amps squared times R2, which is 2 ohms. That power is then 14.3 watts. And the power through R4, we do it the same way, I4 squared R4. Well, the current through R2 is going to be the same as the current through R4, 2.67 amps squared times 4 ohms, or 28.5 watts. So we found all of them very quickly like that. Alternatively, you could break this, go back and rebuild the circuit and find the current through each one of these two resistors in parallel and use power equals I squared R to calculate it, but we did it a quicker way. So the next problem, a beam consists of 5 types of ions, A, B, C, D, and E, enter a region that comes to uniform magnetic field, feels perpendicular to the plane of paper, but its precise direction is not given. So it could be up or it could be down. They all travel with the same speed. So label each path with the ion that travels along it, right? A, B, C, next to the numbers above. Well, one thing I note is that let's say you have a positive particle coming in and the field is into the page, for example. So a positive particle would go left, negative particle would go right, if we assume that the field is into the page, but we don't know. But we do know that left or right is what determines whether it goes left or right is the charge of the ion. And we know that there are 3 positive charged ions and 2 negatively charged ions. So therefore, these have to all be the positive and these have to be negative based on just counting them, right? So if the force pushes the positive charge to the left and the velocity is upwards in the page, then the field must be down into the paper. So velocity, curl in the direction of the field, thumb points in the direction of the force. Velocity is this direction, field is into the page. So that's actually part B. I answered that first. Into page. We know these are the positive ions. We know that they have the same charge. So the difference is going to be the mass. If it has a larger mass, it's going to be heavier, harder to move. So it's going to move with this big arc C. And of course, stepping down in units of mass, PA. A has the smallest mass. So given the same amount of force, it's going to be curved really, it's going to have a very small radius of curvature because it's going to accelerate more quickly. Or think about it in terms of centripetal forces mv squared over r, as if the force is the same in each case, as m goes up, r must also go up. So C is the largest mass, so C is the largest radius of curvature. So determine the magnitude of the field if ion A travels in a semicircular path of radius 0.5 meters at a speed of that. So R equals 0.50 meters, and the speed, magnitude of the velocity, is 5.0 times 10 to the 6th meters per second. So FB equals QV cross B. The magnitude of the magnetic force then is just QVB, and, well, sine of theta if you wish, but this is going to be 1 because theta is 90 degrees. Velocity is up. Magnetic field is perpendicular to the paper, into the paper. And we also know this is the only force acting, so this becomes the net force, which then equals MA. So QVB equals mass times acceleration, but the acceleration here is the centripetal acceleration, so it's v squared over r. Some canceling here. QB equals mv over r. And we're solving for magnetic field, so B equals mv over qr. And we are looking at ion A. So ion A has a positive E charge, and the mass is 2 units. So 2 times 1 mass unit, which is 1.67 times 10 to the negative 27 kilograms. Oops, can't see what I'm writing. Times the velocity given above over E to R. If you calculate that out, you get 0.209 Tesla. An electron is accelerated through some potential difference and enters a uniform magnetic field. So if we say an electron, negatively charged particle, is accelerated through some potential difference. So if we're just drawing this up, we'd say that's the negative side and that's the positive side because we're accelerating an electron. We have the voltage. This is delta V. And we have the magnetic field. Okay, so what are the maximum and minimum possible values of the magnitude of the magnetic force? So Lorentz force law says QV cross B is magnetic force. We're going to come back to this, but first we need to find the velocity with which it enters the magnetic field here. How are we going to do that? Well, my mind maybe goes to, you can go several different ways. Probably the easiest thing is to say that work of conservative force is equal to the negative change in potential energy. That's always true. In this case, the conservative force is the electric force, so this equals the negative change in potential energy, and that equals the negative Q, the negative is just carried over, delta V. So as the electron is accelerated, QV must be greater than 0. The change in potential going from here to here must be greater than 0 because it's an electron. So an electron is going to accelerate towards areas of higher potential, so it's increasing potential as it moves. And the charge is less than 0, obviously, because it's an electron. So this is negative times negative E delta V. The work then is equal to plus E delta V. And we know one other true statement is that the total work done on some object is equal to its change in kinetic energy. So then E delta V is equal to K final minus K initial. It's accelerated from rest, initial equals 0. So 1/2 mv final squared is equal to E delta V, or V final is just equal to the square root of 2E delta V over m, where m is the mass of an electron. So we have the change in voltage, we have the charge of an electron, we have the mass of the electron, we have final velocity. So going back here, we're just asking about the magnitude. So the magnitude of FB is QVB sine of theta. FB max then must equal QVB because it is maximum when theta equals 90 degrees. When theta equals 90 degrees, this term equals 1. FB minimum is just 0 because when theta equals 0 degrees, sine of theta must equal 0. If we have this value for sure, and FB max I can just go back and plug in for V, so that's Q times the square root of 2E delta V over m, so the mass of an electron, times the magnetic field B. And you can plug that in. And 0.209 Tesla. So the final question says you have some wire of length 75 grams per meter. So this is, it's basically like a linear density, right? So this is going to be mass per unit length, or 0.075 kilograms, I just converted to kilograms, per unit meter, per 1 meter. Or I can just write 0.075 kilograms per meter. Okay, and we have current equals 0.62 A. What's the magnetic field strength? Okay, so I've got this wire. It's running horizontally, and it's at a right angle to the magnetic field, to a horizontal magnetic field. So let's say the wire is running across the table, the magnetic field points upward at a right angle, the force points up, gravity pulls downward. But I'm going to draw it from a different angle. This is from the side view, whereas let's say this is the ground. So current is in this direction. The magnetic field is therefore into the page. Like let's say this is traveling east and the magnetic field is traveling north. We have the force of gravity working on it, and we have the magnetic force working upwards. So the sum of all the forces then is just the force of the magnetic force working upwards minus the force of gravity, which works downward. It's floating there, so they sum to 0. Or you could write it like to be complete, mass times acceleration equals 0. And this is in the y direction. Nothing's happening in the z direction. So the magnetic force equals the gravitational force. The magnitude of the magnetic force is QVB sine of theta, but we know that everything's at right angles, so this is going to be 1. QV, that is coulombs times meters per second. Well, that's the same thing as if we have IL, which is coulombs per second times meters. All right, so if we have a current running through a wire, that is our expression. And this equals mass times gravity. The total mass of the wire times gravitational force. So we need to solve for B, so that's mg over IL. We don't have the total mass, and we don't have the total length. But what do we have? If we have G over I, we have M over L. All I did was move stuff around, and what do you know? M over L were given explicitly up here. So B is equal to 9.8 meters per second squared over 0.62 amps times M over L, which is 0.075 kilograms per meter. So you can plug that in and you get your 0.119 Tesla.